Good morning, everyone. Welcome back. So we're going to be working on some triple integrals today. And the main thing we're going to focus on is setting up these integrals. So the spot we ended off with last lecture was we were talking about what questions we need to ask ourselves when setting up a triple integral. So this is an integral over a spatial region rather than what double integrals is an integral over a planar region. So now we're integrating over space. And the things we need to ask ourselves are, so we're referring to the diagram down in the bottom left corner. We want to integrate over that region E, that sort of blue blob shaped region. We need to ask ourselves, what is the footprint or what is the shadow that that region casts in the various coordinate planes? And we pick the one, we pick the footprint that gives us the best shot at setting up an integral efficiently. And so in this case, the shadow that's projected by E into the x2, x3 plane is shown there. It's called footprint D. And so that means that our first variable of integration, or the innermost integral of the innermost variable of integration, in other words, the variable we will integrate with respect to first, is going to be perpendicular to that footprint. So it's going to be along the x1 direction. And then once we've set that up, then the remaining two integrals are going to be to integrate over that region D, that planar region D. So we'll get some practice in setting these things up now. So we'll go and do a number of examples. And I want you to just keep in mind that the thing that we are focusing on is the setting up of the integral. That's where all our effort's going to really go into. It's setting up that integral. The evaluation of the integral, in these cases, they're all fairly basic integrands with limits of integration that we can certainly work out the integrals for. So that becomes then an exercise in integration. But our main emphasis here is on setting up the integral in the first place. That's where the challenge really resides. The evaluation of the integral is just doing three integrals from Calc 2, for example, one after the other. But the setting up of the integral is the new thing. So let's have a look at what this particular question is asking us. So we want to evaluate the triple integral. So the integral over this spatial region E of this function square root of y squared plus z squared. So in setting up these integrals, it's always the region that we're focusing on. It's never the integrand. The integrand we will deal with after we've set the integral up and we actually want to go and start computing it. Right now, we're always going to be focusing on this region E. So let's get a feel for what this region E looks like. So we'll give a bit of a sketch here. Might need to move this over because I'm going to run out of along the x-axis. So what does our region look like? So there's x, y, and z. So it's bounded by this paraboloid, x equals y squared plus z squared. So that's a paraboloid that's opening along the x-axis. Its two traces are essentially the intersections with the xy plane, for example, is just a parabola y equals x squared, and then the intersection with the xz plane is x equals z squared. So we get some shape that sort of looks like this. Let's see if we can get a drawing of this. So there's our paraboloid. Opening along the x-axis. So I'm just going to extend this x-axis a little bit further so it comes out of the paraboloid. Here we go. Dotted line is supposed to indicate that we're looking through the upper part of the surface to see that dotted line on the lower part of the surface. So I guess since we can see through there, we can make that a little bit solid there, because now there's nothing preventing us from seeing it because we chopped it off. So there's our paraboloid, and we want it to be bounded by the paraboloid and the plane x equals 4. So if we indicate there's x equals 4, then it's going to be trapped between this end cap, if you want to think of it as an end cap, or this cap on the paraboloid and the stuff inside. Okay, so this is really what my drawing has captured. We've got an end cap there at x equals 4, and that's the paraboloid we are sketching in our diagram. And what we are interested in is integrating over the region that's bounded by the paraboloid and this end cap plane. So we want to integrate over the inside of this entire solid. So we're integrating over the inside of it. So we're integrating over all x, y, and z values inside that paraboloid. Okay, so then we got to go back to those questions, and we've got to think. First question, what is the footprint, shadow, or projection of our region in the coordinate plane if we're going to integrate with respect to x1 first? What's the shadow in the other coordinate plane by the other two variables? This will dictate which variable we want to integrate with respect to first. So what I'm going to do is I'm just going to drag across our visualization. So this, for the later examples, we'll just do it straight from our picture, but I want you to get a feel for what it is we're looking for. So what it is I'm looking for is I've got this region here. I just want to see what is the shadow that it casts on each coordinate plane. So for example, if I look down along the Z direction, so there's the Z direction, I'm looking down along it. This is essentially the shadow that's cast. So I'll turn off the shape and I'll just leave the shadow there. There's the shadow. I'll drag it around so you can see it. I'll get rid of this. Oh, not that one. I'll get rid of this one. So there's the shadow that would have cast. That paraboloid would have cast onto the XY plane. So if I am choosing to integrate over the over the Z direction first, then this would be the second two integrals I'd have to integrate over. I'd have to integrate over this region. So this would be a Z first integral, and that would be the shadow or projection or footprint I need to integrate over. Let's turn back on our solid. And I'll turn on our end cap and I'll get rid of that footprint. What else could we do? Well, we could integrate along the X direction first. And if I integrate along the X direction, then I'd basically be integrating from a point on the paraboloid out to X equals 4. That would be my X direction first. And then I need that to sweep out the entire region. That means I'd have to figure out what the shadow cast by this shape is on the YZ coordinate plane. And so I'm using these as sort of a visual, because this is what we want to do for all of our examples. So what would the visual be? Well, I'd imagine the shape casting a shadow. And so I just imagine in my head what the shadow would look like if I was to cast that shape all the way down. And so there's the shadow. In other words, if I look at it from this way, this is the shadow that shape will cast. So that would be the region that I need to integrate over. If I do my X integral first, then I need to integrate over this region second. That would be the planar region in the end that I'd be integrating over. Okay, so then the question is really having to decide which one is more beneficial for us to do. Now, at this point, you haven't really done any examples of triple integrals yet, so it might not see that one's more beneficial to do over the other. So we'll get a feel for actually doing one of these setups, and then we'll see how that compares with the other direction. So what we're going to do is we're going to do an x1 first integral, and that means this is the shadow I'm going to look at integrating over next. So an x1 first integral. So that's what we're going to do. We're going to mark that down. That's our note. we're going to do an x, I called it x1, but x first integral. So our x first integral. What is the answers to our question? 1a, what is our footprint or shadow? And since we're doing x1 first, this is the footprint or shadow in the YZ plane. And this is going to be a disk. So D is a disk in the x equals 0 plane, in other words, the YZ plane. And let's get a sketch of that. We'll sketch it down below here. This is YZ. I will draw the shadow in our picture above first, just to get a feel for where it's sitting. It's sitting here. It's just that shape that got projected into the x equals 0 plane. So that is our resulting shadow. That's what we're calling D. And what is it? Well, we need to know, so it's a circle. How do we know it's a circle? Well, the reason we know it's a circle is because what we are doing is we are essentially taking this end cap, which is what's creating that shadow essentially, this end cap out here. And what is that end cap? That end cap is the intersection of the plane x equals 4 with the paraboloid. So that end cap is we take the equation of the paraboloid and plug in x equals 4. And so we get a circular disk of radius 4. So this is y squared plus x squared is equal to 4. So it has radius. Sorry, I might have said radius 4, but I meant to say radius 2. So it's a circular disk of radius 2. So that's our footprint. That was 1a. I've just written it down as 1 as a disk, but when we answer question 2, we'll be a little bit more specific. So what's the next part? Question 1b. Scroll up. 1b is saying, are all the sides parallel to the x1 direction? So in this case, x direction. In other words, let's figure out what the sides of this shape are. So how do we determine sides? Well, the way we determine a side is we just think, are there any line segments that are parallel to the x-axis that are living on the boundary of this region? And because this is a paraboloid, it's all curved. It's all curving in. And so there are no sides to this shape. There's, if you want to think about, well, there's got to be sides. Well, we're breaking this up into, are there sides? That is, things that are parallel to the x direction. And are there, 1C will ask the question, what is the top and bottom? And it turns out that this thing is going to just be all top and all bottom. The paraboloid is going to be the bottom, and the planar cap on the end is going to be the top. So there are no sides to this. 1C, what is our top and bottom? Well, we've got, now again, it's about perspective. Did I write something wrong? Oh, yes, sorry, I did, thank you. That Z got transcribed incorrectly. That should be a Z there. Thanks for catching that. Okay, so what about the bottom and the top? I'm going to drag our object across. So bottom, top, those are all relative to the x first direction, because that's the direction we're integrating with respect to first. So we're talking about what is the bottom in the x direction, what is the top in the x direction. And top always means there are higher x values, so the x values are larger. So I'm really thinking about this as sort of situated like this, with the x direction going, sort of moving in that positive direction. So the bottom, if I'm now thinking of this as a shape, all this blue stuff is the bottom. It's like my bowl that's containing a bunch of liquid, and the top is this end cap. So the bottom is the smaller x values all the way up to the top, which it consists of the larger x values. And there are no sides to this object. There's only bottom, which is the paraboloid, and top, which is the end cap. So let's jot those things down. So we've got our top and bottom. What are those things? Well, the way I like to write them down is always as an inequality. So x, what's the smallest it is? What's the largest it is? So what are those x values in the region trapped between? They are trapped between the paraboloid, y squared plus z squared. So in other words, that's the bottom, because those are the smaller values. And they are trapped above by 4. In other words, that's the top. So we've got our x values are trapped between those two regions. And then we can go on and answer question number 2 of our, called them 4 questions to ask. They're really grouped into 2 types. One is all about the 3-dimensional region. Once we've dealt with that, which are the first 3 questions, that's why they're grouped together as type 1 questions. They're all about the 3-dimensional region. Now in type 2, that's now going about the 2-dimensional part. So once we figured out we're going to integrate along x first, we've set all the information up we needed. And then part 2 is to say, what do we do for that 2-dimensional region? So that's going to be that disk we identified in part 1a. So this is our 2D region. That's our disk D. And it's a disk D of radius 2. So it's that y squared plus z squared is equal to 4. And at this point, I'll just scroll up. Question 2 is really not about identifying the region, because we've already identified the footprint or shadow in 1a. It's really about, what is our integration plan? Now, what do we plan to do with integrating? Once we've done the first integral, the x integral, now we need to do the yz part of the integral. How do we do that? Well, what's our integration plan for this region? Well, this is now integrating over a disk. Now we're into a double integral. And so our integration plan would be to go to polar coordinates, because it's a disk now. And so our polar coordinate plan would be, we take y is equal to r cos theta, and z is equal to r sine theta. And so there is our setup. That's our full plan for how we're going to deal with this. Okay, I'm going to have to insert a piece of paper in here. I think actually I need to copy, and I need to get the background right. So that's why I need to copy and then paste. Otherwise, it'll give me just a white page as a background. So there we go. Okay. So I got my extra page in there. Now we're going to go ahead and do the setup of the integral. So I'm going to leave our questions up above. And the integral is now this triple integral over E of our integrand, y squared plus z squared dv. And now we're going to go and say, well, we set it up as an x first integral. So that's going to be our innermost integral, our x values that we're integrating over. And then following that x first integral, we're then going to do the integral over the footprint. So that's our integral over d, which I'll just write as the integral over d dA, because that's going to be our area integral. So the idea is, with these triple integrals, we're setting up one integral for the first variable we choose to integrate over on the inside, and then the remaining stuff is just a double integral. It's back to section 15.2. 15.2, 15.3. It's those just the double integral stuff. But all of that setup that we've just done, questions 1A, B, C, and question 2, was to figure out which variables we're going to integrate with respect to first, and how we're going to deal with the multivariable integral. Okay, so now let's go and fill in the rest of the details.
I have a quick question.
Yeah, go for it.
About part A. So when it says footprint shadows in YZ plane, what happens like if your function has all X, Y, and Z? Like then how do we choose which plane to look at?
So, I mean, ours does have, so the function in terms of which function? Because we got a bunch of them here. Do you mean the integrand?
Yeah.
So that didn't actually matter. I didn't care that the integrand didn't have an X or a Y or a Z, or I'm not even looking at the integrand when I do any of this setup, because this whole setup is all about trying to make sense of the region E. The integrand makes no difference really at this point. The integrand doesn't come into play until we start to actually do the evaluation. So the only reason I chose to do the X first integral wasn't because I looked at the integrand and saw an X missing there. The only reason I chose to do an X first integral was because when I looked at the shadow that it projected a circle onto the YZ plane. And I thought to myself, yeah, I can deal with circles. I know how to integrate over circles. But also, when I look at the X direction integral, I'll be integrating over line segments like this that start on the paraboloid and go out to X equals 4. So I know my X values are just trapped between these two values here, on the paraboloid and up to 4. And because my X value in this direction is trapped between those two things, those are going to be my limits of integration. So those were really it was after doing these questions that we're like, okay, yeah, we're in good shape. If I was to do the integration, say, along the Z direction first, so I have to go along the Z direction, that means I'm going to have to figure out what is my lowest Z value. And I'll drag the image back over here. What is my lowest Z value? What is my highest Z value? And that all depends on where I am along these curves. So
could we still do that? Like, because when I initially looked at the question, I thought it would also make sense to look down. Like, say you were above the Z plane, and then you look down, and then it just looks like a parabola with like a plane at X equals 4, which it is.
Yeah, so you're thinking, yeah, why don't I make the integral over this region as my outer integral? And then that means when I do the first integral, which is the Z integral, I have to go from here up to here. And so I need to go from the lower Z value, which would be, remember, this is a paraboloid, so these are going to be, these are basically, this is an equation, X equals Y squared plus Z squared. So then I have to take that equation. Where are we here? I'll take this equation. And I have to say, okay, what's my smallest Z value? Well, my smallest Z value would be, I'd have to solve this then. That would be 4 minus Y squared square root. And it would go from minus, the bottom down here would be minus the square root of 4 minus Y squared. And then the top up here would be the square root of 4 minus Y squared. So those would be my upper and lower half paraboloids, if you will. And those would be the Z values I'd be integrating between. So if I did this direction, I'd have to introduce square roots, for example.
Right. Okay, so then that's not doable.
Yeah, those are more challenging to deal with when we integrate. It's not impossible, but it's certainly, it could be done, perhaps. You would only find out by setting it up. But this way, when I did the X first, I could avoid square roots altogether.
So basically for us, it probably is easiest to look at, like, we can look at multiple directions. Like, we can look at the shadow in Z, shadow in X, but just kind of pick the simplest shape.
You got it. Yep. Pick the one that gives you the simplest answer to these 4 questions. So it's likely you're going to be answering these 4 questions multiple times to decide which direction you want to go first. Yeah, thanks for that question. So now we've got our integral partially set up. We're going to just work out what are the x limits of integration, and those come from this question about bottom and top. So our x values are going to go from y squared plus z squared all the way up to 4. And so that's all questions. This is what questions 1 through 1A, 1B, and 1C gave us, was this initial setup. We knew what the innermost variable of integration was. That's the x. That was our x first integral. We know what the limits of integration are. Those are our bottoms and tops. And now we can go ahead and attack the outer integral. That's our area integral, and that's what question 2 allowed us to answer. So our outer integral, and I will just keep these things separate for purposes of focusing on what we're doing. The outer integral, we are going to use polar coordinates, and we're integrating over that purple region D. So for polar coordinates, our area element becomes r dr d theta. So that's because we're doing polar coordinates. We have to change our area element to represent the polar area element. And then our r's and our thetas, they are ranging from r goes from 0 to 2, and theta goes from 0 to 2 pi. And that'll sweep out the area region. And I'm not quite done yet, because when I do this change, I have to change this to polar as well. Change to polar 2. Right? If I'm doing an integral that I'm changing my x and y, or my y and z values into polar coordinates, then I've also got to make sure I do that for the integrand. So I'll just fill in a couple more things here, the upper and lower limits of integration. And then we're going to change that inner thing to polar 2. So what I am going to do is I'm going to do that right in the spot here by just...
Is your integrand going to be just r squared now?
Which one?
Your lower limit.
Oh, yes. Yeah. So once we do this change, we'll get those updated. Yeah, thank you. So this one, we're going to change to polar. And so that becomes a square root of r squared. So that will become just an r, essentially. And we've also got to change our limits of integration to polar as well. So in this case, this becomes an r squared. And our upper one is still just 4, because x is ranging from r squared now up to 4. And so we've got all of our changes made, our updates to polar coordinates, and now we'll just write down the last line, which sort of takes into account the fact that we have a square root of an r squared. So there's our limits of integration. Square root of r squared just becomes an r. And we've got another r that's outside. So that becomes an r squared dx dr d theta. And so that's our integral that we want to calculate. And this integral, it's just 3 of them back to back. So we don't really need to do an exercise in integration. I will say that there's a couple of things that you can do that allows you to save some time. If you look at the first integral, it's an x integral, and there's no x present in the integrand. So this is basically a constant with respect to x. You could always push the r out front. So I'll just give you some hints, things to look for. It's not always going to be the case, but it is worth observing when you can push constants out. So this would be r squared.
R squared again instead of r.
Say that again.
You wrote r squared.
In terms and as the integrand.
Yes.
Yeah, because there's another r out front.
Oh, okay.
Right. Don't ever forget about that r from the polar coordinate change. Yeah. So there's that sneaky little r that comes in because of the area element. This guy out front, or out back, I guess I should say. So that one came in together with the square root of r squared to join together to give us an r squared. And then this integral becomes a 4 minus r squared And so then we're the integral from 0 to 2 pi, the integral from 0 to 2 of 4r squared minus r to the 4th dr d theta. Notice there's no theta anywhere. So this is theta free. And so that means it's a constant relative to theta. So we can always do that theta integral as a separate integral from the r integral, minus r to the 4th dr. I really haven't done any integrals yet. If you kind of think about it, I haven't done any integrals, really. I haven't done any antiderivatives. I'm just noticing that things are constant. And so the theta one, the theta integral becomes 2 pi. And so we're left with just this integral here, r to the 4th dr, which you can then evaluate. It's an integral polynomial. I'll leave the details for you to evaluate. But I want to show you it's not, the key here is not essentially the integrals. That's not the difficult part. The integrals are just, you do 3 integrals from Calc 2 nested inside one another. And sometimes if you just notice make some observations that things are constant relative to certain variables, then you can split the integrals up and make them even simpler. And in this case, there's really only one integral to compute because the other ones were just integrals of a constant. And so that one integral was the r integral. The challenge is the setup. And the setup is really what we as humans are here for. We're solving problems, integrals come up. It's our job to set up the integrals. We are never, in our future courses, in our future work, in your whatever profession you get into, you're probably never going to evaluate an integral by hand. But you are, for certain, depending on your area that you go into for a profession, for example, if you're in engineering, you will be setting up integrals. You will be setting up integrals. And that's the challenge. You got to set up the integral that solves your problem. And once the integrals are set up that are going to solve your problem, then you'll have a computer actually do the integration for you. But it's the setup, that's the human endeavor. So if you're ever working on this going, oh, this is so challenging setting up the integrals. Can't I just have it already set up? And it's like, well, no, because the integration part, that's the mechanical part. It's the setup. That's the part that we need to be able to do. Okay, so let's have a look at the next example. And then, well, we've got a couple more examples to compute, but I just want to make the connection that just like we had in our applications of double integrals, we get the same kinds of things coming up in triple integrals. So we can work out mass, centers of mass, moments of inertia, all for solids now. Before we were doing them for planar lamina, so plates essentially with varying densities. We can do the same thing now for regions or for solid objects. And the mass is just the triple integral of the density function over the solid itself. So that's a triple integral, integrating over all the points that make up the solid. Centroids and moments of inertia are all defined the same as well. Just natural generalization up one dimension. So let's go ahead and do another example. Let's find the mass of the solid T, which is given by, which has a density function of rho, which is x plus y. So the density only depends on the xy coordinates, not the z coordinate of a point making up the surface, or sorry, the solid. And T is the region that's trapped between surfaces z equals 2 minus x squared and z equals x squared, where y is trapped between 0 and 3. So we'll get a sketch of this. So what is this going to look like? Well, again, these are both shapes we can recognize. You notice that there's a y variable missing. So these are going to be cylinders in the y direction. We just need to plot them in the xz plane first, and then just translate them in the y direction. So this is a parabola that's opening downwards and has a y value of, yeah, y value sorry, a z value of 2, highest value. So there's our z axes, and there's our x axes, and there's our y. So we got a z value of 2, so it looks something like this. It's a parabola that's opening down. And we've got another parabola, z equals x squared. So that's a parabola that's opening up. And they're going to meet somewhere in the middle. So we got one parabola opening down, one parabola opening up, and they're going to meet somewhere in the middle, something like that. And that's going to be translated along the y direction. So we still have this upside down parabola and this right side up parabola. And so there's our region that we're interested in. So this is our solid. This top one is z is equal to 2 minus x squared, and this bottom one is z is equal to x squared. And at this point, we'd like to figure out what direction should we integrate over first. So we've got some choices. We can integrate over the z direction first. In this case, I'd be looking at the shadow that this object projects onto the xy plane. And the shadow is essentially the cross section, the biggest cross section that sort of encompasses the whole region. And we can see that's sort of that center rectangle. There's that rectangle right in the middle of it, and that's the shadow that would get projected down below. So if we did a z first, so a z first integral, then our footprint is going to be, we've got y, we've got x, and our footprint is going to be this rectangle. Maybe I'll draw it in a different color just to indicate where it's coming from. It's this rectangle here, just pushed down, because that's what's going to cause the shadow down below. So it's out here at a distance of 3 along the y-axis. And what is the distance along the x-axis? How do we figure out how wide this rectangle is? Any ideas?
Your intersection points.
You got it, yeah. So we got to look at our intersection points. So we've got the intersection of z is equal to 2 minus x squared and z is equal to x squared is, setting the z's equal to each other, we get x squared is equal to 2 minus x squared, or in other words, 2x squared is equal to 2, or in other words, x is plus or minus 1. So we've got -1 and a +1. So those are our x values. And that's the region, that's that 2D region we are interested in. I've essentially already worked out the answer to question 2 in some sense, because I've got all the information I need to integrate over this region. So it's a rectangle, so we're integrating over a rectangle. And that's nice. I mean, if we just think about it from this perspective, we do z first. Our outer integral, the double integral, is a rectangle integral. So it's a rectangular integral. So we got constants of integration for constant limits of integration for our x and y values. So this might be sufficient at this point to say, yeah, I'm going with it. I'm going with a z first, as long as I can make sure my z values are trapped between things that I can work with. So let's go ahead and finish off our answers to these questions. So 1a, the shadow is a rectangle in the xy plane. So we got that drawn already. 1b, are there sides? So are there sides? So we're looking in the Z direction. Sides are going to be things that if I imagine I take a line segment in the Z direction, so I'm imagining my pencil as a line segment in the Z direction, and I just sort of move it around all the boundary part of the shape. Is there ever a place on this object when I'm on the boundary, which the entire pencil is going to lie on the boundary? Are there any, in other words, are there any straight boundary sides to this? Straight boundary sides. Really, the idea of the word sides is that it's indicating something's going to be straight, parallel to the Z axis. And yeah, there are sides. I'll sketch them in, maybe I'll use pink here. Here's sides. So I just draw line segments and I'm like, oh, all these line segments are parallel to the Z axis and they make up one side. All these ones make up another side. So yes, there are sides to this shape. So sides, yep, we've got a couple. We've got the y equals 0 side, and we've got the y equals 3 side. Now, one of the key things to note about sides is they can't depend on the variable z. They shouldn't have z in them. If you're writing down expressions for the sides, they shouldn't involve a z, because the idea is the entire line segment, regardless of the z value on this line segment, it's supposed to be sitting on the side. So the sides are independent of z value. So these, just a note here, there's no z variable. That's an indicator of a side. So if you're looking at sides and you write down something and you've got a z in it, then you know something's gone wrong, because sides are independent of the z value. They are straight lines along the z direction that
Are
live
you just
on the
saying z
boundary.
because that's part of the function? Like if say it was like x equals 2 minus y squared, then it would be x. There's no x variable.
So are you referring to this function when you said function? The density
I guess
function?
I'm just wondering, why is it always, no matter what, the z variable?
Nope,
Or does it
because
depend on it totally depends on our function?
it's z first. So if you're ever wondering about what reference in terms of variable I'm making, it's always because we are doing a z first integral right now. So
Okay.
because it's a z first integral, our first direction that we're going to integrate along is the z direction. So my sides of my object are going to be related to that direction. Do I have sides in this z direction? Yeah, so it's always in relation to that z first. Just like the shadow is related to the z first. If I'm integrating along the z direction first, my shadow is in the xy plane, and my sides are going to be parallel to the z axis.
Okay.
So I will say sides parallel. Oh, there's no T in that. I don't know why I crossed that. Parallel to Z, and that's because of that Z axis. So that's what I'm interested in when I'm talking about sides. What are the boundaries, parts of the boundary that are parallel to the Z axis? Okay, and so maybe I'll just add a little bit more to this. The reason that I'm interested in these sides, for example, is because when I do a z first integral, what I'm integrating along is I'm integrating along the z direction. So I pick some point down in my domain, in my shadow, and then I go up from that point, find out when I hit the bottom of the surface, and I integrate along all the values until I hit the top of the surface. So I'm imagining that I'm doing something like this. So there's my sort of cross section there. And I'd be integrating over this pink line segment. So this pink line segment goes from the lowest z value to the highest z value over top of a particular point xy in my shadow. And then I integrate over the entire pink line, that's integrate over my z values. And then I let that pink line segment go over all xy values over the entire footprint. And that gives me a way to sweep out all points in the region, integrating over all points in the region. So I integrate along over a particular XY value up the Z axis, and then let XY sweep out all of the points in the shadow, and that gives me all the points in the region. And so the reason I'm interested in sides is because that's when that entire line segment is sitting on the boundary, when I'm integrating over a boundary. And that's those two end caps. So then 1C is going to be our bottom top. And again, these are in reference to Z. So bottom and top are what are our Z values trapped between. The bottom is going to be the lower parabola, which is x squared, and the top is our upper parabola, 2 minus x squared. And so there's our bottom top. And then our question number 2 is about our 2D region. And our 2D region consists of the rectangle, which has values x between -1 and 1, and y between 0 and 3. So when we structure, so I should back up and say, these questions, as we've laid out in the notes here, they are not done in the textbook. So the textbook sort of ignores these individual questions and it just motors on through and sets up the integral. However, years of teaching Calculus 2, we've found that it's a challenge to figure out how to set up these regions. So we want to break it down into small steps, small bite-sized steps. And these are the small bite-sized steps, these 4 steps to go through to figure out what the region is. Start with a variable you're going to integrate with respect to first. Structure your first 3 questions based on that. Find the projection, the shadow that it's cast onto the coordinate plane of the other 2 variables. And then go ahead and set up what are your sides, what are your bottoms and tops, and then how do you integrate over the remaining 2D region. Once we do this, a lot of stuff starts to fall out. For example, these are all the limits of integration that we need. Those are all our limits of integration. They're right there, all ready for us to use. So when we go ahead and we set up the integral, so we're finding a mass here. So the mass is going to be the integral, the triple integral over t of the density function, x, y, z, dv, our volume integral. We've got our integration variables now. So we've got our outermost ones. Our innermost one, our z, is going to go from x squared to 2 minus x squared. And that's going to be our density function, which is x plus y, dz. So that's our innermost integral. You don't have to put these parentheses in. I'm just doing it for emphasis on these first few examples. Then our outermost integral is to integrate over a rectangle. And since we're integrating over a rectangle, it doesn't matter which order we do the integral in. So maybe I'll do dy and then dx. So y is 0. Oh, sorry, I see that something happened here. Did something cut out?
Yes. The last thing we were at was when you were starting to define the 3 integrals.
Okay. So let's get rid of this.
Your screen share died.
My screen share died. Everything's going wrong today. Okay, let's see. There we go. Everyone can see that?
Yeah, you did a lot while we were gone.
I was motoring. All right. Let's get rid of this. So we were about right here, is that right?
Yeah.
Okay. So then we're going to set up our integral. We've got our 3 integrals that we're going to do. And that's where we look at our limits of integration. So our innermost one is z. We've got the limits of integration from x squared to 2 minus x squared. And that's our density function, which again, x plus y. I never worry about the integrand until this point. So now this is our Z first integral. And then the outer integrals are the ones we're doing now. So the outer integrals we can do in either order because it's a rectangle. So I'll go dy dx. And then that y value goes from 0 to 3, and the x value goes from -1 to 1. And so that's our integral. So we've done the setup. And I'll just write down the final result, because at this point it's an exercise in integration. And if we do the integral, we'll get a value of 12. So that was our Z first integral. We could do other directions as well. There's no reason we had to go with a Z first. I just went with a Z first because the projection was a rectangle, and that was quite nice. But we could have done another integral. I mean, another integral might have been to do a Y first integral. Because if we do a Y first integral, we're integrating along the Y direction, then our shadow is going to be just that region trapped between the two parabolas in the XZ plane. So maybe I'll just take 1 minute to set this up. What about, let's say, Y first? So if we do a Y first integral, then we'll redraw our region. It's going to look like that, like that. And like that. And if we're doing a Y first, it means our footprint is going to be this shape down here in X, Z is our upper axis. So it's going to be a shape that looks like this, parabola with another parabola. And so that's going to be our shadow. And we've got an upper curve for this. That's our Z is equal to 2 minus x squared. And we've got our lower curve, which is our Z equals x squared. And the other thing to observe is that there are sides on this now. There's a top and a bottom, but the top and the bottom, we're thinking of this thing moving along the Y direction because we're doing Y first. So this would be the top. Maybe I'll put that in a different color. That's our top. This is our bottom. And our sides are going to be the parts of the boundary that are parallel to the Y-axis. So our sides are basically everything that's wrapping around. So those are our sides. And I'll leave these 4 questions for you to set up. We will come back to these 4 questions on Monday, and I'll set them up for this one. But I just want you to think about trying to go through and answering these 4 questions. We've already set up most of this. 1A, we've got our region there. What are our sides? How can you write the equations down that represent the sides? What's our top? What's our bottom? Those are going to be the limits on the Y, the lower bound, the upper bound on Y. And what is our integral that's going to represent this shape, or the integral over this region? So I'll leave it for you to think about, and then we'll answer these questions on Monday. All right, I'll stop the recording.